Okay, let's talk about this question here. An airplane flies eastward and always accelerates at a constant rate at one position along its path. It has the speed. Okay, so what it's doing is it's flying, and it has 34.9 meters per second at this point, continues flying another 48,100 meters, and then has a velocity of 43.5 meters per second. So it went from an initial velocity of 34.9, final at 43.5. So you can use v final squared is equal to v0 squared plus 2ax. Your initial velocity is 34.9. Your final velocity is 43.5. Your distance is 48,100. Solve for a. That'll be your acceleration. Once you have your acceleration, you can do v equals v0 plus at to solve for the time. Okay, delete. Next. 45. After big snowfall, you take your favorite rocket-powered sled out to a wide field. The field is 179 meters across, and you know that your sled accelerates at this rate. How much time will it take the sled to cross the field? Okay, so we have 179 meter field with this acceleration. So we've got an x, we've got an a, and we want to know a t. So we're going to say that we're going to travel, starting from rest, a distance of 179 meters at a rate of 3.85 meters per second. So we can say our distance that we're going to travel is going to equal 1/2 at squared because we have no initial velocity, so plus v0 x is going to be 0, and our initial x0 is going to be 0. So we just have this equation, x is 1/2 at squared. So then we solve for the t. So time is going to be 2x over a, square root that. 2 times 179 divided by our acceleration, okay? And then how fast will it be moving? Then we can just, once we have our t, v final is going to be at, because our initial velocity is 0. And then how fast will it be moving halfway? We'll just plug in where t is half, and you'll get your half your velocity. And if you are under constant acceleration, velocity versus time looks like this. So whatever your final and your initial velocity is halfway, you just half the velocity. Okay, done with that. Delete. Next. Small bag of sand released from a hot air balloon. Okay, so this one, you've got a hot air balloon basket, and the hot air balloon is moving up, and then when it drops the bag of sand, the balloon in the next, if I imagine time a little bit later, the balloon will be up here, and initially the sand will be rising up with it, so we dropped it, so there it is, we just pushed it out. It'll continue to rise from that point and then fall, okay, because it has an initial velocity up. So this would be the same thing as taking a bag of sand, throwing it up with an initial velocity of 2.45 meters per second. Okay, initial velocity 2.45 meters per second, and then from there it'll just do regular motion. So the bag of sand being thrown up from the hot air balloon is trying to psych you out a little. It's the same as just throwing an object up in the air and watching what happens. So let's look at it a little more closely. Okay, so there's our initial velocity. It's going to go up, come back down, and I'm expanding it out. I'm drawing it like this, even though it's only moving in one dimension, just to make it a little more clear. So we're going to divide this problem into two pieces because we know our initial velocity here of 2.45 meters per second. We know at the top of this v equals 0 meters per second. We can call it v final up there if we want. And then when we get back to this point, our velocity is going to be 2.45 meters per second, and then we will accelerate from there until we hit the bottom. The question is how long it's going to take, and one indication is this tau symbol instead of t. We're going to imagine that that tau refers to the total time, which will be the time for this above this black line to occur, and then plus t2, the time it takes to fall the rest of the way. So we're going to divide this problem up into two parts. The first part is that motion. The second part is that motion. Okay, just regular falling, and then this one is a parabolic toss. Okay, so we know for this first part, if we just look at this part, we are going to say our initial velocity, because we're trying to find the time, v final equals 0. V initial is equal to 2.45 meters per second. Gravity is, or our acceleration is negative 9.81 meters per second squared. Okay, so I'm just going to say that the time it takes to go from here back to here, so from here to here, V final is equal to V initial plus GT. Okay, and so V final is 0, so we're going to have is equal to 2.45 meters per second plus 9.81 meters per second squared times t. Okay, this is minus because 9.81 is negative, and then when you bring the 2.45 over to this side, it becomes negative 2, so you end up with two positive numbers, and you can solve for the time there, and that will be the time to do that first part. So we now have the time it's going to take the bag of sand to go up and down. Okay, so that would be t1. We just figured that out. Then the next part is we've got an initial velocity here of 2.45 meters per second, actually negative because it's moving down, and it's going to fall after it goes up and comes down. It's going to continue to fall until it hits the ground. How long is it going to take? Well, we've got 73.8 meters here. How long is anything going to take to fall 73.8 meters if given that initial velocity here? Well, we can say that the distance y that it's going to fall, we know 73.8 meters equals our initial velocity v0 times time plus 1/2 gt squared. Okay, so this would become 73.8 meters is equal to 2.45 meters per second minus 9.81 over 2, so that's going to become minus 4.9 meters per second squared times t squared. Okay, and so this, and then we've got a t in there. So this equation here, if I rewrite it to make it look a little bit nicer, this equation here, I'm going to have, I'm going to bring the 73.8, I'm going to bring it to that side. Okay, so I'm going to have 0 is equal to negative 73.8 meters minus, because our initial velocity is actually in the negative direction, minus 2.45 meters per second times t minus 4.9 meters per second squared times t squared. Okay, so that, let me rewrite it so you can actually see the whole equation. I want to be certain that you can see the whole thing. So we're going to have 0, let me write it down here. Okay, we're going to have 0 is equal to minus 73.8 meters minus 2.45 meters per second times t minus 4.9 meters per second squared times t squared. Okay, so now we have A, B, and C here. This is a quadratic formula, so you can use a quadratic formula calculator if you want online, where you just plug in A, B, and C. So A would equal minus 4.9. A is the value in front of the t squared. B is equal to negative 2.45. That is the value in front of the t. And then C is equal to negative 73.8 meters. And that is your initial height that you're starting from. Your final is going to be 0. And so that's why we're going to fall negative 73.8 meters. Okay, so those three numbers you can plug into the quadratic formula solver and get your answer for t. Okay, that's what the quadratic formula solves, is what is t, so that when you plug in a number into t, you get 0. Okay, so 73.8 minus 2.45 meters per second times what minus 4.9 meters per second squared times what squared will end up canceling all that stuff out and just give you 0. Okay, if you plug in those numbers there, you got your formula, opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So you can do it manually or you can do it in the calculator. Okay, that's, if you get good at that, that's the easiest way to solve this problem. There's another way that might be easier for you if you're afraid of using the quadratic formula. Okay, and that is you just solve two equations. So we're going to travel 73.8 meters down. So you can have v final squared is equal to v initial squared plus 2ax, or 2ay in this case. So you can figure out what your final velocity is just before it hits the ground. V final squared is equal to 2.45 meters per second squared, and you can put the minus sign on there, but when you square it, it cancels out. And then minus 9.8 times 2, minus 2g times 73.8 meters, okay? And then times g will give you meters squared per second squared. Take the square root of all that, you'll get your final velocity, and then you can say, because you want to know the time, you can say v final is equal to v initial plus 2at, okay? Sorry, not 2at, just plus at, and then you can solve for the time there. So v final minus v initial divided by acceleration will be the time it takes to fall from here to here. So there's two ways to solve for the second time. One way is just to use one equation and then solve the quadratic formula to get it. The second way is to solve these two equations to get the final velocity and then calculate the time it takes to fall. Okay, so the main thing of this problem though, T1, T2, divide the problem up into a simple single up and down where it ends at the same height. You can do all the math there easily to calculate the time. Okay, importantly, I think I ignored this. The time you solve for this upper part is just here to here, so make sure you do 2 times that t to get the rest of the time. So it's going to be t plus t plus t. Okay, delete screenshot. All right, next one. Okay, on Venus, the acceleration due to gravity is 8.87 meters per second squared. How far would a 39-gram rock fall from rest in 4.5 seconds if the only force acting on it was due to gravity? Okay, so y equals 1/2 at squared. Yes, we can use that one. Why? Because we're dropping it from rest, so there's no the plus v0 t plus x0. We're starting from rest, so that's 0. We're starting at 0, x equals 0, so there's no offset. So we can just use this equation. How far would it fall? So how far? It's going to be 1/2 times g on Venus, which is 8.87 meters per second squared. Similar gravity to Earth, you'd feel a little bit lighter, but not much, times 4.5 seconds squared. Boom. You get seconds squared here, cancels out the second squared there, and you get meters, and that's what you want, and that's how far you'd fall on Venus in that time. Okay. While standing on the edge of the roof of a building, a man throws a stone upward with an initial speed of 7.57 meters per second. The stone subsequently falls to the ground, which is 17.9 meters below where the stone leaves his hand. What speed does the stone impact the ground? Okay, so we've got a guy throwing a projectile or a stone upward, and then it falls to the ground the rest of the way. Okay, it's 17.9 meters during that trip. We're going to go ahead and ignore this whole upper thing because we don't care about it, because we know the initial velocity here equals the initial velocity there. When you toss something up, it comes back down, and when it passes the point where you tossed it up, it's the same speed. Okay, so what speed does it impact the ground? V final equals V initial plus 2ax. Sorry, V final squared is equal to V initial squared plus 2ax, or 2ay. Okay, 2ay. So the final velocity that it hits the ground is going to be equal to 7.57 meters per second squared plus, in this case, minus 2 times 9.81 meters per second squared times 17.9 meters. Boom. Square root all that. Okay? That's going to give you the final velocity just before it hits the ground. Okay? How long is it in the air? Then you can do V final equals V initial plus AT, and you can solve for T. So V final minus V initial over G is going to be your T. Okay? Delete that. Next. Okay, you throw a baseball directly upward with an initial velocity of 12.7 meters per second. What is the maximum height the ball reaches above where it leaves your hands? Okay, you're going to throw the ball up in the air. What's the maximum height? V final squared is equal to V initial squared plus 2GY. V final is 0 at the top of the trajectory. V initial, 12.7 meters per second squared. Okay, and then plus, in this case, minus 2 times 9.81 meters per second squared times y. Solve for y. That's going to be the height, the maximum height that you get. At what time does the ball pass through half the maximum height? So we want to go halfway there. Okay, so what we can do is go to y equals 1/2 at squared plus v0t plus y0, which is going to be 0. So we can go to that equation, plug in half the maximum height, and then use the quadratic formula to solve for half the t. Or we can, that's one way to do it. or we can, so you'd be solving the quadratic formula for t when y is half of its height. Okay, remember when you're solving the quadratic formula, any quadratic has a shape like this. There's 2 points near where the x value and the y value intersect like that. Okay, x, y, okay? So when you're solving that formula, you're solving for what is this value at that point. That's what the quadratic formula allows you to do. At this y value, what is x? At this y value, what is x? So for that y value, you get 2 x values. That's why. So that's what's going on with the quadratic formula. So just as a reminder. Okay, but what we want is the time for half the height. So there's 2 here, and that's what, if you solve the quadratic formula, you're going to get 2 heights there. So plug those values in because the at what time does the ball pass through half height? As it goes up, bink, it's going to pass it. As it comes back down, boom, it's going to pass it. So solve the quadratic formula for y is half the maximum. And then, so how do you do that? Again, so we'll have y is equal to 1/2 at squared plus v0t. And so to get the quadratic formula in the right format, we're going to have 0 is equal to at squared plus bt plus c. So we're going to have 0 is equal to negative 4.9 t squared plus 12.7 t, and then minus our max height, whatever that ends up being, y. In this case, we want y over 2, okay, to get our maximum height. So negative 4.9 is a, 12.7 is b, and negative y over 2 is c. So you put those things together into the quadratic formula, and you'll get 2 values. T is equal to plus or minus blah. And that's, you put the shorter time here and the longer time there. Okay, delete. All right. A runner is training for an upcoming race. In order to track the pace of the runner is able to record time splits for the entire period. This allows the runner to produce the given velocity versus time graph. The run is broken into 6 segments. Assume the run is in a straight line. Answer the questions concerning this graph. Okay, so let's take a look. The average acceleration of the runner during segment 1 is, in this case, the velocity versus time is constant. It's 3 that whole time. So v final minus v initial, 3 minus 3 is 0. So there's no acceleration in segment 1. Calculate the average accelerations A2 and A6 of the runner during segments A2 and A6. Enter both the magnitude and direction. Okay, so in segment 2 and segment 6, both of those segments, I don't know if there's more to this problem, it's not letting me scroll down, but in 2 and 6, they both have a positive acceleration, right? They're both speeding up, and what you care about is the slope of that line. So we went up 0.25, 0.5, 0.75, so we went from 3 to 3.75. That was our rise. So we're going to have 0.75 meters per second was our change in velocity, divided by 5, 10, 15, 20, 25 seconds, because we went from 10 to 35, 25 seconds. So that is our acceleration there, and we're going to do the same thing here. We went up 0.25 meters per second over a time of 5, 10, 15, 20. Okay, so then that's your acceleration during that time. Okay, delete that screenshot, and those are the problems. Okay, next. Public transportation bus makes the position time graph over a 5-hour interval shown in the graph below. There are 4 segments in the total trip. What are the average velocities v1 and v4 of the bus intervals during the intervals 1 and 4? Okay, so we're looking at this position versus time graph. Let's see. There are 4 segments. What are the average velocities? Okay, so average velocities. So in this case, the velocity, okay, this is a very jerky trip. It's going this fast, this fast, this fast. There's no acceleration. It's just changing velocities very fast. If there was an acceleration, this would have a smoother line. Okay, so this is a little bit of a spiky trip. All right, so remember, the velocity is the rate of change of position. So you're going to do the rise over run here. You're going from 15 is your final, minus 40, that's your initial, divided by the time, 1 hour. Okay, so you're going to have negative 25, right, kilometers over an hour, 1 hour. So your velocity is negative 25 kilometers per hour during this stretch, and then in stretch 4, you're going to do your final is 60 minus your initial 40 divided by the time. Looks like 2 hours. 2 hours. So that's going to be 60 minus 40 is 20 over 2, 10 kilometers per hour. Positive. Okay, delete. Next. John is rollerblading down a long straight path at 0. The mailbox is in front of him, a meter. 5 seconds, blah, blah, blah. You have this. Okay. Assuming the things are, what is John's position at the time of 4.47 seconds? Okay, so what you're going to do is drag these things around. All right, so the mailbox is 1 meter in front of him. So that means he's starting, because this, taking the mailbox to mark the 0 location. So that's where the mailbox is, and it's 1 meter in front of him. So that means he's starting at this point. Okay, so this is a confusing problem, but you have to start there. So you start where you are, which is 1 meter in front of the mailbox. Okay, then we go to the velocity versus time graph to see how he changes from there. He moves away from the box 1 second, 2 meters per second. So he travels at 2 meters per second for 1 second, so that means he moves 2 meters away. So that means in the next second, he's down here. He should be down at negative 3 meters because he moved 2 meters away. Then he sits there for 1 second, doesn't move, bonk, no velocity. Then he goes forward 2, so up and over. So he goes to there, and then to there, and then to there, okay, because he's travels 2 meters, 2 meters, 2 meters. 2 meters per second times 1 second is 2 meters. 2 meters per second times 1 second, 2 meters per second times 1 second is 2 meters. So you get 2 meter change, 2 meter change here, 2 meters of area, and that gives you your distance. So the area of this curve gives you the amount of change in that curve. So you should have a graph that looks like that. Delete. Okie dokie. 53. Given any 2 vectors, which statement is correct? I don't know, just deal with that. Okay, so we've got these vectors all have the same length but point in different directions as shown. Each vector is added to vector A. Okay, arrange them from longest to shortest. Okay, so vectors B, C, and D all have the same length but point in different directions. Each vector is added to A. Arrange the... Okay, so A and B are added together. There's your resultant. In this case, there's your resultant, and in this case, there's your resultant. Okay, so which one's shortest and longest? A plus B looks to be the shortest, A plus D is the next shortest, and A plus C is the longest. Okay, delete. Next, Adam drops a ball from the top of a building at the same location which hits the ground first. Since they're both dropping and horizontally, they both hit the ground at the same time. Zookeeper is trying to shoot a monkey sitting on top of the tree with a tranquilizer gun. If the monkey drops from the tree at the same instant the zookeeper fires, where should the zookeeper aim if he wants to hit the monkey? Okay, aim straight at the monkey. This is a weird thing, but it's a common thing you're going to deal with. You got a monkey in a tree, okay, and you're down here, you're trying to, okay, you're not trying to hurt it, you're just trying to protect it, so you need to give it a tranquilizer. So when it drops, as soon as you launch the projectile will start falling at the same rate that the monkey falls. So it'll go up and then it'll fall at the same time that this is. So by the time the monkey's here, it will hit it. And that's the idea. You have to aim directly at the monkey when you launch it. So my velocity vector should look more like that. So aim directly at the object, right, and then shoot right as it falls, and then you will hit it every time. Okay? If you try to aim above it, you're going to miss it. If you try to aim below it, you're going to miss it. And that's because it's falling at the same rate. Okay? A ball is thrown into the air and follows the parabolic path indicated by the dashed line. Use the arrows provided to indicate the approximate directions of the velocity of the ball at each location. Okay, so you shoot a basket. Acceleration is always down. That's g. The velocity vector is always pointing in that in the direction of the trajectory at that point. And there's an x and a y component, and x and a y component, and x and a y component. Okay, the x component is the same length throughout the flight. The y component goes from up to 0 to down. Okay, so maybe this is the top of the trajectory. So the velocity vector will be straight over. The net velocity vector will be straight over, so I'll draw that as black like the other ones. Okay, and because the x component is there and the y component is 0, and then our y component over there is like that. Okay, so acceleration always down, so this is just making sure you understand the differences there. Delete. Okie dokie. Vector A is a magnitude 9.5, direction 203 clockwise from the x-axis. Okay, so let's draw an axis. Vector A is a magnitude 19.5 and its direction is 230 degrees, so we know that's 180, and we know that this is 270, so it's somewhere here. Okay, so this angle is going to be 230 minus 180, so that'll be a 50-degree angle, because if that's 180 degrees and that's 230 degrees, then the difference of them should be this angle, and that's what we want. And so now we know that the length of this is 19.5, and we want to know the components of it from the positive x direction. Okay, so we're going to have a negative x and a negative y component to this vector. The x component is going to be the adjacent over the hypotenuse, so the x component of this vector is going to be 19.5 times the cosine of 50 degrees, because that's our angle, that's our adjacent side, that's our hypotenuse, and the y component is going to be 19.5 times the sine of 50 degrees, and that's going to tell us that component of it. Okay, and then you also know that x squared plus y squared should equal 19.5 squared. So you could find x first and then solve for y using that, or continue with the trig. Okay, next one. Farmer builds 3 sections of a fence shown in the figure. Gets tired, walking straight back to how far did he go? So he goes 30, and then 30, and then 15, because it's L over 2. Okay, and then he's going to go back home. How far did he go? Well, he's got to travel 30, and then he's got to travel whatever this extra distance is. Okay, so we know the side of this triangle is L over 2. So where's our right triangle? Look for it. There it is. We want that side. How far does he have to go? He's going to go L over 2 squared plus whatever the distance here is, d squared, is equal to 30 squared. So d is going to be the square root of 30 squared minus L over 2 squared. That'll give you this distance. Then, oh, there's already a little d in here. Okay, so there's a little d there. Forget about it. That's what we're trying to solve for. Let's call this big D, I guess. Big D. Big D. Big D. Okay, so then total distance, this little distance is going to be d, whatever distance we find there, plus 30, this side of the thing. So he's going to walk this far, and then he's going to walk that far. That far is just this side of this right triangle. Okay, and so then you get total distance of whatever that works out to be. Delete. So that's just making sure you get your triangles. Okay, you got a two-dimensional vector here. The x component A is negative 9.6, the y component 7.65. What is the magnitude of this vector? Okay, x component, bink. Let's draw that. There's the x component, negative 9.60. Y component is 7.65. Let me draw a different color, 7.65. All right, what is the magnitude? That's easy. The magnitude, let's call it m. The magnitude, m of this vector, is equal to the square root of 7.65 squared plus 9.60 squared. Okay, it would be negative 9.60 squared, but when you square a negative, it becomes a positive. Okay, so then you've got, now, I mean, that's it. That's the answer. Done. Delete. Next. 61. Vector A has components ax equals negative 5.6, 15.6, and 11. What is the magnitude of the vector? Okay, again, 15.6 squared plus 11 squared. Square root it will give you the magnitude of that vector. You've got x and y components. The magnitude is the Pythagorean theorem of that vector. Okay, you put that in here. Find the angle between the vector and the x-axis. So here's your vector. There's the x component. Oops, we've got a negative x component, so let's draw our coordinate system. We've got a negative x component and a positive y component. So our vector is here. So we've got negative 15.6 here. We've got 11 here. What is this angle there between the vector and the x-axis. We could do tangent. Tangent of this angle is equal to 11, opposite over adjacent, negative 15.6. Okay, theta is going to equal the arc tangent of negative 11 over 15.6. Okay, and that should give you the angle of that triangle. Okay, next, delete. Blah. Vector C has a magnitude of, okay, so we've done this one in class a bunch. So what we do with this one, we want to know what are the magnitudes of A and B, these two vectors, A and B. Okay, we know alpha, beta. So how we do this, we have to solve a system of equations. So AX, that's AX, BX, BX. Then we have AY and BY. Those are the components. We know that AX minus BX is equal to 0. So that means AX is equal to BX. Okay? AX, if we add the vector AX plus BX together, then we get 0. So AX is equal to the opposite of BX. Okay? So they are the same size, basically. And then we also know that AY plus BY is equal to, plus C is equal to 0. So if we add AY, add BY, and add C together, they should all add up to give you 0. Okay, so that means AY plus BY should equal the magnitude of C, but they'll be opposite to it. Okay, so then what are the magnitudes of them? So how do we figure this out? Well, first thing we do is rewrite the two equations into their components, because we know what alpha and beta are. So then AX is going to be A cosine of alpha, and then minus or equal to minus B cosine of beta. And then we know that A, if we do the other equation, A sine of alpha plus B sine of beta, and then plus C is equal to 0. Okay, then what we can do is say that A is equal to minus B cosine of beta divided by cosine of alpha. Okay, and that's our A value. We're going to grab that and substitute it in here to get rid of any A's in this equation. And that means we can solve it. And so we'll have minus B cosine beta over cosine alpha times sine of alpha plus B sine of beta plus C equals 0. Okay, now this looks complicated, but it's not, because we know what C is. C is 28.2 meters, so we know that number C, how big C is. Okay, we also know what sine of beta is, because beta is known. We also know what all these sines and cosines are, so just calculate it. Cosine of 26.7 degrees, that's a number. Divide by cosine of 42.9 degrees, that's a number. Times sine of 42.9 degrees, that's a number. Then just solve for what B is. Okay, it's a little bit of algebra, but then you get the answer. Okay. All right, you got a plane, releases a ball as it flies parallel to the ground at a height of 205 meters as shown in figure. If the ball lands on the ground h, which is the same height as it is, calculate the speed of the plane. Neglect any effects due to air resistance. So we know h is 205 meters. Now the thing is, the time it takes to fall here is the distance it's going to travel here times, rate times time equals distance. So its initial velocity, or its velocity in the x direction, times the time that it's falling is equal to the distance that it travels, h. Okay, how far does it travel? We know that it travels 205 meters because it tells us that the height is 205 meters and that they're the same. So we've got one equation here, and we know that the time it takes to fall here, let's do y equals 1/2 gt squared, because it's falling from rest. So we can get that the time is equal to 2y over g square root. It's going to fall 205 meters. Okay, 205 meters. 2 times that over 9.8 meters per second squared. technically the y will be negative 205 meters and g will be negative 9.8, which is good because now our square root is positive. You always need a positive underneath the square root because you don't want to deal with complex numbers and taking the square root of a negative number. Okay, so you can calculate how, using the fact that the height is 205 meters, you can calculate how long it takes to fall. Once you have that, you can, once you know how long it takes to fall, then you can say v0x is equal to 205 meters divided by t, and then that tells you how fast it must have been going in order to make that happen. So we use the fact that this dimension is independent of that dimension. We use the time it takes to fall here to know that that's the same amount of time we had available to travel 205 meters, and then rate times time is distance. Okay, delete. All right, cannon is mounted on a tower above the ground. Barrel of the cannon is 20 meters above the ground. A cannonball is fired horizontally with an initial speed of 800 meters per second. Assuming air resistance can be neglected, approximately how long will the cannonball be in flight before it hits the ground? Okay, so we've got cannonball here shooting initially out that way. It's 20 meters above the ground. Cannonball is fired horizontally 800 meters per second. How long will it hit? Okay, the time it is in the air is simply how long it takes to fall 20 meters because its initial velocity is only in the horizontal direction. So how long is it in the air? Y is 1/2 at squared. 20 meters times 2 times 20 meters over negative 9.81 meters per second squared, and then we're going to fall negative 20 meters, so that's a negative square root of that. That's the time it's in the air, equals t. Okay, that's the time it's in the air. Simple. It's just falling out of the sky. All right. Then the next thing, how far from the base of the tower will the cannonball land? Well, that's easy. Now we know how much time it's in the air. We just solve for t, and 800 meters per second times t is going to be the distance that it is able to travel before it hits the ground. Okay, and then that's it. Same as the previous problem. All right, next. Projectile is launched from ground level with an initial speed of 43.5 meters per second and an angle of 34.5 degrees above the horizontal. Strikes the target in the air 1.66 seconds later. What is the horizontal distance from where the projectile was launched to where it hits the target? Okay, we're launched from ground level. Boom. At an angle 34.5 degrees above the horizontal. It strikes a target in the air 1.6 seconds later. So strikes the target at t equals 1.66 seconds. What is the horizontal distance from where the projectile was launched to where it hits the target? So we want to know, oops, I did not want to erase all that. We want to know, okay, there's our initial velocity, 43.5 meters per second. We want to know how far over did it hit that target? Well, this is easy. We just say we want to know the x component of our velocity. The x component of our velocity times time is going to equal the distance that we travel until we hit that point, r in this case. We want the range. Okay, so that's just v0 cosine theta times 1.66 seconds is going to be the range. That's going to tell you how far it traveled. We want the x component, and that's our hypotenuse, that's our x component, adjacent over hypotenuse, that's cosine, ka, so ka, toa, okay, adjacent over hypotenuse. Okay, what is the vertical distance from where the projectile was launched to where it hits the target? So now we want to know how high is it in the air at that point, and we can say y equals 1/2 at squared plus v0t, and then we can solve for y at t equals 1.66 seconds with an initial velocity of the y component, which would be v0 sine theta. So then you just plug everything in there, and you'll get the value, the height at that time, 1.66 seconds. Okay, delete. Next. Projectile is fired at 368 meters per second, an angle of theta here. Okay. With respect to the horizontal, assume that air friction will shorten the range by 35.1%. How far will the projectile travel? Okay, so what we're going to do is figure out the range and then multiply it by 0.351 because it will shorten it. So what do we have to do? We've got our initial velocity of 368 meters per second. Gravity immediately starts bending that arrow and pulling it back to the ground. That's what gravity does. It accelerates it. Okay, what we need to do is figure out the time it takes to go from here to there. Okay, so that's our first step. So how do we do that? First, we find the y component. v0y is equal to v sine theta. v0 sine theta. So that's our initial y component. So if it's 368 meters per second, 368 meters per second times the sine of 63.3 degrees, it should be a number between 0 and 1. Anytime you have sine theta, you have a number between 0 and 1. So that means it gives you some percentage of the initial velocity. And that makes sense. It's less than 368. Then you say, okay, well, how long is that going to take to get to the top of this thing? Well, we'll say v final equals 0, because at the top of this, v final equals 0. So we're going to have v final squared. No, we want the time. So we're going to say v final equals v0 plus at. Now we have our final velocity is 0. Our initial velocity is v0 sine theta plus at. Solve for t. T will be the time it takes to go up here. 2 times time will be the total time you have in the air, which actually helps us determine how far we travel. So that same time, that's 2t, rate times time, so v0x times 2t is going to equal this distance, this range. Okay, so how far will it travel? So we're going to have v0 cosine theta, the x component, times 2 times this time is going to equal the range, and then we're going to take 0.351. We're going to reduce the range by 35%, and that's going to be the distance it travels. Okay. Next. Soldier is tasked with measuring the muzzle velocity of a new rifle. Knowing the principles of projectile motion, he decides to perform a simple experiment in indoor firing range. Soldier hangs a target, shoots it. Bullet exits horizontally. After 6 trials, the soldier tabulates the values he measured. What is the most accurate muzzle velocity the soldier can report to his sergeant? So, what you are going to do is take the average of these displacements. Okay, so that'll be your average height, the average drop there, and then that drop is going to equal, okay, because we know this distance of 114 meters. So take the average drop here, rate v0x times time equals distance. So that means the time it takes to get to the target is going to equal the distance over your initial velocity, v0x. Okay, and then the time that it falls, y is equal to 1/2 at squared. So your average height that you're dropping will give you the average time. Okay, so 2y over g is equal to t, square root that. So average all of these together, that's going to be your average height. Then you can calculate the average time, and then you go back to this equation and say that your most, the average muzzle velocity is going to be distance over this average time that you get from doing that. Okay, delete. Next. Robin would like to shoot an orange in a tree with a bow and arrow. The orange has the thing like this. Okay, this is a really tricky problem. Let's go here. Oops. Yeah, okay, so the orange is hanging 5 meters above the ground. So there's your orange, 5 meters. On the first try, Robin shoots the arrow at an initial velocity of 31 meters per second at an angle of 30 degrees. Above the horizontal, the arrow has an initial height, so y0 of 1.1 meters here, and the tip is 43 meters away. Treating the arrow as a point projectile and neglecting air resistance, what is the height of the arrow once it reaches the horizontal position x of the orange? So all we need to do is imagine our quadratic function and say, what is the y value at this distance x, okay? So what we have to do is we've got an initial v0, and we want to calculate, okay, how far does it travel? What is the height of it at that time? Okay, so we can say that the height at any given time is equal to 1/2 gt squared plus v0t plus y0. Okay, and this height at any time along this thing is given by this y thing. So our y0 is 1.1 meters. Our initial velocity is v0 sine theta, our component of the velocity in the y direction, and then 1/2 gt squared is just the acceleration that's changing that throughout the trip. So if we can figure out the time to put in here at that point, we can plug that in to get the height at that point. Okay, so what we have to do then is get the time. Okay, and the time, since we know that this is 43 meters, we need to know the time it takes to travel that distance. So we're going to say v0 cosine theta, the x component of the velocity, times time is going to equal 43 meters. So the time it takes to travel that 43 meters is just 43 meters divided by v0 cosine theta. That gives you the time. You go back to that equation I just had down, plug your t in, and that'll give you the height at that point. Y is 1/2 at squared plus v0 yt, and then plus y0. And that'll give you the height of the arrow at that point. Okay? For the second try, he wants to change the position, but shoot the arrow using the same speed and angle as the first try. So now he wants to keep everything the same, but change this distance so that the orange actually gets hit by the arrow. So what he's doing is he's shooting this thing, and initially does it say where it is? Height of the arrow, whatever you saw for it, it ends up, I think he, I don't know, I can't remember if it overshoots or undershoots, but either it overshoots or undershoots. So the idea is he wants to, I think it overshoots, he wants to get closer to keep the same angle, boop, so he either hits it or he wants to get further away so that when he shoots it, it goes up and then comes back down and hits it. So there's two positions he could be because of the quadratic nature of this. He could either be here or there, this whole distance, and with the same initial conditions, he can intercept the orange. Okay, so where does he want to be so that he hits the orange? Well, what you want is that your y is equal to 5 meters. Your final y is 5 meters. So you're going to have 5 meters equals 1/2 at squared plus v0 yt plus y0. Okay? This is what you're solving for. You're going to use the quadratic formula again. So you're going to have 0 is equal to 1/2 gt squared plus v0 sine theta t plus 1.1, that's your initial height, minus 5. So your y0 minus y final at the end there. So what is your a? Negative 4.9. Negative 4.9 t squared plus v0t, v0 sine theta. So it's going to be, in this case, our projectile is in the negative direction. So we're going to have minus 31 meters per second times the sine of 30 degrees. And then minus 1.1 minus 5. Okay, so minus, I'm going to put this, whatever that ends up being, well, it'll be plus, and then 1.1 minus 5 there. Okay, and then there's your A, there's your B, there's your C. Plug that into your quadratic formula, and you get T1 and T2. You get 2 times. Then you just do T1 times V0 cosine theta, that's x1. T2 times V0 cosine theta equals x2. And that's, you can either be this far away or you can be that far away, x1 or x2. That's how you do that one. Delete, next one. Okay, Bob's just finished climbing sheer cliff, blah, blah, blah. So what we want to figure out is how tall this cliff is. Okay, so we've got a cliff. We want to know how tall is it. All right, so we know that we've got an initial velocity here, 34.5 meters per second squared. We also know that at this point in the problem, divided into 2 parts, that velocity here is the same, 34.5 meters per second. But the vector is a little bit different because the y component's negative now. Okay, so what we know is the time it takes to go from here to here. Okay, so what we can figure out then, we know the initial velocity. We can figure out the time it takes to go up here and there. Okay, but that's really not what we care about. What we care about, the main thing we have to do, because we know x is equal to 124 meters here. The main thing we have to do is figure out this distance here. Okay, why? Because we know that v0x is the same throughout the entire trip. Okay, v0x, v0x, v0x. Okay, why does that matter? Because we know the time from here to here, t1. We know that time is 0.51 seconds. What we need to figure out is the time it takes for this projectile to fall, the time it takes to go from here to here. If we can figure that out, if we can figure the time it takes to fall, then we can figure out the height. Okay, so that's our goal. We have to figure out the time. So what we need to do is figure out t2, because we can get the time from here to here. It's given to us. So our main goal now is to figure out the time t2. So we know that v0x rate times total time t1 plus t2 is going to equal this 124 meters, this full distance. Okay, but we also know that v0x times t1 is equal to this distance, d1, let's call it. Okay, d1. All right, so we're going to have v0x times t1 plus v0x times t2 is equal to 124 meters. That's just saying rate times time plus rate times time equals distance. All right, so now we can say that t2, the time it takes to go from here, t2 is equal to 124 meters minus d1, whatever this distance ends up being. Now we have this distance, okay, divided by v0x, your initial velocity. Okay, if you do that, you can figure out this time. Then, using that time, you know what your just y equals 1/2 gt squared plus v0 yt plus y0. Our final velocity, our final height here is going to be 0 because we're going to hit the ground. So you're going to solve for y0, how high you started with. Okay, then the only thing that's left is to figure out v0y, and you figure that out using a simple, the half, it's 0.51 seconds to go up and down, so that over 2 is here. So then you can figure out how long it would, what initial velocity, v final is equal to v0 plus at. You can say v0y is equal to at, and you know that this is 0.51 seconds over 2, and your acceleration is 9.8, so you can get v0y, which is the same v0y here, and that's the v0y you put there, and boom, you solve for what y0 is, the height of the cliff. Okay, a lot going on there, but just take your time and write neatly on a giant piece of paper. You can write crayon on your wall, for example. Okay, next one. Near the end of a marathon race, first two runners are separated by a distance of 35 meters. The front runner has a velocity of 3.25 meters per second, and the second runner has a velocity of 4.75 meters per second. What is the magnitude of the velocity of the second runner relative to the first? Okay, so you got one person running here, another one running here. This runner has 3.25 meters per second. This runner has 4.75 meters per second. So according to this guy's running up on him, getting close to him. So the difference is 1.5 meters per second. If the front runner is 215 meters from the finish line, who will win the race, assuming both runners run at constant velocity? Okay, so what you're going to do now, they're both 215 meters. So you're going to solve for the time. 3.25 meters per second times time equals 215 meters, and 4.75 meters per second times time is equal to not 215 but 215 plus 35 meters. Okay, why? Because the second runner is 35 meters away. I might have done that backwards. The front runner has a velocity of 3.25 meters per second. Yeah, so that guy only has to travel 215 meters. This guy's got to travel 215 plus 35 meters. So for T1, T2, whoever has the shorter time wins. By what distance does the winning runner finish? Then you'll be able to, the difference in time will tell you the distance that separates them. So just solve for that. Okay, next one. During 9.19 seconds, the motorcycle changes the velocity from this to that and this to that. Find the components. Okay, this is easy. You just do the problem twice. You've got a time of 9.19 seconds. The acceleration in the x velocity is final x, v final x minus v initial x over t. Okay, so our final x velocity is negative 17.1. Our initial x velocity is negative 39.5. So minus a negative becomes a positive, divided by 9.9 seconds. Okay, do that. A y is equal to v v, yeah, final y minus v initial y over t. Where's the v final y? 29.1 meters per second minus 14.5 meters per second, and so on. Okay. Yada yada yada. Da, 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 da. Okay. Okay. Next. Starting from a location with this vector, a rabbit hops around for this many time. Average velocity is this. Find the components of the position vector, the rabbit's final location, R2, R1. Okay, so you're going to have one vector and another vector. And so what we're going to do is compare the x components and the y components. So starting with a location of negative 12.1 meters in the x direction times time, 13.9 seconds. No, not that, sorry. 12.1 meters, okay? And then it hops around for 13.9 seconds with an average velocity of this. So that's your initial thing. Then we're adding 13.9 seconds times negative 2.71 meters per second. That's a distance in the x direction. So that's our final x coordinate, because we started here and we added rate times time to get a new distance, and then you do the same for the y dimension. Okay, and then we got a turtle ambling leisurely, as turtles do, from this position to that, with the position vector of that, where the lettuce appears to be tastier, it's not, whatever. Excursion takes 347 seconds to complete. What are the components and the magnitude of the turtle's average velocity? Okay, you do the same thing, rate over time. So rate times time is distance for x, rate times time is distance for y, and just solve for that. Speedboat moves on a lake with initial velocity of this, and accelerates for that. What are the components of the final velocity? Okay, you're doing the same thing. You've got an initial velocity vector with an x and a y component. Your acceleration is going to change the x and change the y components to give you a new velocity vector. So we can just do them independently. V1 is 8.45 meters per second. The acceleration is, in the x direction, negative 0.104 meters per second squared. Okay, what is the component of the final velocity? And we're doing it for 5.23 seconds. So v final is equal to v initial plus acceleration times time. So our final x velocity is our initial x velocity, 8.45 meters per second, minus 0.104 meters per second squared times 5.23 seconds. Boom, that's our new x velocity component. And then we'll do the same thing for y. And then what is the final speed? That's going to be v final y squared plus v initial y squared. V final x squared, square root, because we're going to have an x and a y, and we want our new component, the magnitude of it. Okay, 75. Fox locates rodents under the snow by the sound they make. The fox leaps straight in the air. Okay, so the fox is going to go whoop, boom, and hit the snow. Okay, so gets up a height of 0.75 meters. The acceleration is negative 9.81 meters per second squared. V0 is something. V final at the top of this peak is equal to 0. So what we want to do is calculate the speed, V0, that leaves the snow, and the amount of time in the air. So V final squared is equal to V initial squared plus 2GY. So our final velocity is 0. Our initial velocity is what we want, minus 2 times 9.81 meters per second squared times 75 centimeters. So we're going to have V0 is equal to the square root of 2GY. And then you can figure out your initial velocity. And then the time you're in the air is V final equals V0 plus AT. Solve for T. That'll be half the height. Double it to get the total time. Okay, delete. Okay, pitching machine programmed to pitch baseballs horizontally at speed of 87, mounted on a truck. Okay, so speed of the pitching machine relative to the truck. So this and the truck are moving at the same velocity, 55 miles an hour down the road. Okay, so that should be 0. The speed of the pitch ball relative to the truck. So you're going to, so the pitching machine will launch it at 87. The truck is driving at 55, so those two should add together and give you a fast pitch. Okay, and then the speed of the pitching machine relative to the man it should be the speed of the truck, and then the speed of the pitch ball relative to the man should be whatever that ends up being added together. Okay, and then next, scientific method. Okay, yeah, you can do that. That's back to the beginning. All right, bye.